Good. So now it's my pleasure then to introduce the second team, Team Explorer, who will present their mission concept just now. Please welcome them with a warm round of applause.
So before we get started, I really want to thank Simon and Fabian for putting so much effort into planning this whole week. We've also gotten a lot of hours from mentors, some of which are judging us. And I would also want to thank our sponsors. I think we should give all of those a round of applause. And finally, I want to thank the other team for giving us such spirited competition. And with that, we want to share with you our mission.
Are we alone? On this big, vibrant planet, are we alone? On this tiny, pale blue dot, are we alone? For centuries, this is a question that's driven exploration on our own planet and beyond. On this vibrant ocean world, are we alone? On our liquid water ocean world, there is hydrogen, carbon, oxygen, nitrogen, 4 ingredients characterizing life as we currently understand it. We have energy and redox conditions that create incredible and diverse habitats. In the depths of the ocean, ecosystems thrive kilometers under the surface. In the depths of the ocean, where the sun's rays cannot penetrate, the genesis of life on Earth may have occurred. At the subsurface-surface interface, where energy and nutrients erupt from below, we have thriving ecosystems. Over 1 billion kilometers away, we have another ocean world, Enceladus. A beautiful, dynamic ocean world where hydrogen, carbon, oxygen, nitrogen are literally exploding from the interior liquid ocean. So are we alone? It is scary if the answer is no, but perhaps it is even scarier if the answer is yes. Here at Team Explorer, we believe that the scariest of all is never daring to ask this question and never daring to answer it. Today, we invite you on a journey with Etna, a bold, innovative mission to escape our own ocean world and explore another. With Etna, we will assess the habitability of Enceladus and search for biotic and prebiotic biosignatures from oceanic material that is analyzed both in flight as well as for the very first time on the surface. Enceladus is one of Saturn's moons and is about 500 kilometers in diameter. Beneath the surface of relatively fresh, clean water ice is a dynamically interesting body that awaits our exploration. In the center of the body is a core hot enough to allow for intermantle melting. The core is concealed from the subsurface with a nearly 40-kilometer thick ice shell, but close to the South Pole, the ocean approaches the surface within about 4 kilometers. However, today we do not understand the internal structures and how these allow for the habitability of the planet. The surface itself is the brightest in our solar system and marked by these large tectonic scars that extend across the ice. The presence of tectonic features is of particular astrobiological interest because it can foster activity between water-rock interfaces, creating gradients that provide free energy for life. This process is observed on our own planet at the deep hydrothermal vents at the ocean floor. However, today we do not understand whether these tectonic or other forces are actively working on Enceladus and how these are influencing the oceanic systems. We do know that something is driving oceanic materials from the interior of the moon, and these materials contain key ingredients characteristic of life. However, today we do not understand the composition of these plumes well enough to assess between prebiotic, biotic, and abiotic signatures. Etna addresses these unknowns by responding directly to driving questions posed in the most recent decadal survey. And the first objective, where we'll be answering the building new worlds, we specifically address how planetary accretion can affect volatile migration and delivery, as well as the internal dynamics of these worlds. Secondly, in the planetary habitats objective, we assess how contemporary habitats elsewhere in the solar system have conditions and energy and redox reactions that sustain life. Although there are other icy bodies in the solar system, Enceladus is unique to answer these questions. Some of these moons are extinct or dormant. And of the remaining 3 moons, only one provides direct sample access to the interior oceanic materials. This is Enceladus. The driving science questions for our mission framework are divided into 2 major goals. And the first, we ask, how does Enceladus provide habitable conditions? And the second, we ask, what biotic or abiotic signatures characterize Enceladus? In the first goal, we specifically look at how the dynamics of the energy sources can sustain the origin and the biology of life. We also ask how the chemistry and the bulk composition of the subsurface constrain the habitability conditions. And finally, we look at the periodicity and the lifetime of any habitable conditions that may be present in characterizing this moon. Our second goal is focused on biotic and abiotic signatures. Specifically, we'll be observing the composition, structure, and ratio of different subsurface molecules that are key to identifying biotic materials. We will also be looking at the extent to which visual biomarkers characterize the internal oceanic materials. And finally, we will be asking how these key ingredients of life that have already been observed are produced. To explain how we'll be addressing these goals, I'd like to introduce CK, who will be talking about our mission architecture.
Okay, so I'm going to quickly walk through the full mission architecture of Etna. And of course, one of the first questions you have is, how do you get to Enceladus? But it's not enough just to get to Enceladus. You need to get there at a time where you can actually perform all of your science objectives. So on the left here, you have something that may be more familiar to people looking at interplanetary trajectories. We have sort of the trade space of delta V cost versus time of flight versus when you actually get there. And so, we of course could pick a single point down here. Let's say you just want to maximize delta V. But there's a lot of different considerations that need to go into your full mission design. So what we've done is we've baselined a launch a delta V cost of arriving at Saturn of about 1.2 kilometers per second, which puts us in this region here. And we're also going to arrive in about 2037 at Saturn. So what that allows us to do is gives us schedule margin and doesn't put too much burden on meeting specific dates. But the other question is, can you perform the science you need to when you arrive at Enceladus? And so, as the other team discussed, we're arriving at Enceladus' winter, where the South Pole is approaching darkness for the whole second half of the arrival period that we have. So what I'm showing on this plot here on the right is the hours of illumination versus the date. And so you can see the yellow points are this exact southern pole, and that's going to go dark in January of 2039. But at higher latitudes, we actually have a much longer period of time where we can actually operate with visual instrumentation. So our region of interest are these tiger stripes where these plumes are erupting. So we show that we can actually arrive in this half of the arrival window and still accomplish science. So we're baselining a mission that allows us some margin, not only on launch, but also on arrival date. So our baseline arrival at Enceladus is going to be mid-2039. Which brings me to the second point. After we do the gravity assist to take us from Earth to Saturn capture, we're going to do a pump down orbit operation. So we're going to use a sort of novel aerogravity assist using Titan's atmosphere to sort of reduce the delta V it takes from capture into Saturn's orbit all the way down to an Enceladus orbit. So in terms of orbit at Enceladus, so we have Enceladus here. This is some trajectories designed by Diane Davis. And our baseline orbit is this L2 halo orbit highlighted in white. So this is the southern pole of Enceladus. And what this orbit allows us to do is perform much of the science objectives that we need to do, focusing on this southern pole. So it gets us close enough to perform much of our mission operations. We're also going to be doing radio science, not just once we arrive at Enceladus, but in the pump down region before that. So that's going to give us better idea of the ephemeris of the system and improve our mass estimates of Enceladus itself. So our next phase of the mission is mostly operating out of this nominal halo orbit. And now we're going to look at the different science considerations so we can actually answer those questions that Aaron raised. So number one, we're going to look at backlit plume imaging. And this is very similar to the type of imaging that Cassini did. So we'll have visual images of active plumes backlit by the sun. And then we also want to do some localization of plumes because we need to know where these plumes are and ensure that we can find active plumes for our later landing phases of the mission. Next, we're going to do a visual imaging campaign where we not only get high resolution images of fissures in the tiger stripes, but we're also going to characterize where we can actually put our lander. Next, we'll do UV spectrometry, and that's imaging the plume directly to get some more spectral information on that plume. And we're also going to use ice-penetrating radar from orbit, and this is going to give us some more insight into the internal structure of Enceladus. And finally, in the orbital phase, we're going to do a plume fly-through. It's very similar to the Cassini fly-through, where we get a single fly-through a plume at 25-kilometer altitude. And we use a mass spectrometer to actually understand the composition of materials in this plume. But not just to the precision of Cassini, but even better, so we can better understand the chemical composition of these samples. After this orbiter phase, we then have a surface operations phase. And in our concept of operations, we have a main lander and several probes. So the main lander is going to be deployed using propulsively from the orbiter. And this main lander has a mass spectrometer and a microscope. This mass spectrometer is the same mass spectrometer we use in orbit to collect samples from the plume in order to cut down on mass. From this main lander, we want to land within 5 kilometers of an active plume so we can collect fresh samples very close to the plume that we wouldn't be able to get from orbit. We also have a microscope so that we can more carefully analyze these samples. But the main lander also has what we're calling geophones. And these are seismic instruments that can measure the vibrations in the ground. So on descent from the orbiter, the main lander is going to be deploying these into different places on the surface of Enceladus to give us better seismic information on the surface. So the geophones are going to need to record passively for about 1 week to understand the background environment of the seismic conditions on Enceladus. And then we have, so 1 week of passive geophone operation. And then we have a percussive mass that we deploy from orbit. This is going to shock the surface of Enceladus and give us some more understanding of the surface composition using readings from the seismometer. Finally, what we want to do for end of life is dispose of the orbiter into Saturn. And that's going to help us with sort of planetary protection concerns. So here we just have some brief, an overview of how the concept of operations is going to go. Okay, so that's the main lander that just whizzed by. And here's one of those, one of the 3 geophones that we'll have. So when the lander comes down, we're going to have terrain relative navigation as well as infrared imaging, so that in the case that we do have to land at nighttime, we still have the capability to do so. And we also have these wide landing feet so that we can contend with different snow conditions in order to keep the lander from sinking through the surface. If we, in case that we can't characterize the landing site to see that. You'll see up here the collection dish for the ejective from the plume, so that will come up and land in this collector, and then we can distribute it to the different instruments on board. And now I'll transition over to Graciela to tell us about the instruments we have.
All right, so in order to address the diversity of science objectives that such a mission to Enceladus involves, we had to come up with a strategy that will ensure a tight envelope around all the different areas of interest. Here we consider habitability questions, life detectability questions, but also context. And we try to do this in an approach where we reduce the science loss, the science risk, temporarily as we approach into the mission. So we try to gather as much data and context as we are entering the Saturn system, learning more about the plumes, learning more about the surface as we close in, and reducing the amount of context that our lander maneuvers and our lander operations are going to have to conduct in order to complement the knowledge that we will gather in this previous phase. Another important aspect is the fact that we need to ensure that we can cross-validate the interpreted results we will be able to extract from each of the instruments. So we need to ensure there is a certain overlap between the data that each instrument is providing and which phenomena we can then understand and explain by combining the different inputs that we learn from the mission. So I'm going to start with an overview here. As you can see, this is our orbiter platform. And you can see from the top, we're going to be carrying a Cassini-like type of antenna, which has a concentric reflectors. And this antenna is connected to our telecom transponder, but also to an ultra-stable oscillator. We will go into this in a moment. And it's going to help us it's going to help us to learn about the ephemerides of the Saturn system as we go into the flybys. But also, it's going to give us some information about the ionization state of the E-ring of Saturn, and also the numeral density, the number density of the Titan atmosphere, as we need to ensure our aerodrag maneuvers are as limited in uncertainty as possible. As we close in, we will see other instruments taking a primordial role in here, mainly the AROMA, MoMA, mass spectrometer suite. So this is a combination of several instruments. We will go shortly into the details about what we have in this. You need to understand here that the AROMA, MoMA assembly, it's installed in the orbiter model in such a way that it will deploy later as we release the lander, and it will be the same hardware with a different collector system that will perform the measurements in ground after release. Further than that, we can see a very clear antenna boom, about 16 meters in extent, that is the major instrument unit for the ice-penetrating radar. So this is a dual-frequency ice-penetrating radar that is going to give us information on the internal structure of the subsurface, but also altimetry in a different operating mode. At the bottom, we have, of course, a camera system that is a combination of optical and infrared. So we have several channels here that are going to allow us to do a mapping of the surface in the thermal and visible ranges. And of course, there is the IMAG magnetometer, which is going to be performing observations in orbit in order to characterize the magnetic field around Enceladus, with the idea of constraining the dynamo that the Enceladus moon may be creating due to the motion of the ocean mass as it's being excited basically with the spin axis of Enceladus and the tidal forces that may vary this rotation. So going into detail, our radio science investigation, it's an experiment of opportunity that it's mainly using the transponder on the spacecraft on the X-band and Ka band. We have the possibility to vary this instrument in two ways. That's mainly for gravity science, where the uplink will come from a DSN station 70 meters with maser clock stability. And this will allow us to improve ephemeris of the Saturn moons, and therefore improve uncertainty in the size of the maneuvers we will need to perform in order to leverage our orbit down to Enceladus. As we get in, we can also, as I mentioned, constrain the ionization state of the atmosphere of Titan, as well as the possible, not yet fully understood ionization state and distribution of the plumes, as we may find opportunities to enter radio occultation with the plumes. So you see, radio science will give us an improved context as we approach into the mission, where we target actually the main questions of ETNA. Is there a habitability scenario? Are there the conditions for habitability? And a very key instrument is the ultraviolet imaging spectrometer, ALICE, which is a heritage from New Horizons and a previous version on Rosetta, and which is it's a very powerful tool to look at composition of the plumes of Enceladus from a perspective of what kind of macro elements do we see and what kind of dynamics we see in the jets. So this instrument is operating in the 5 to 7 micrometer frequency range, wavelength. It's a relatively compact unit, which basically has a scanner slit that offers us a couple of, exactly 32 scans, if we assume the heritage here from New Horizons, in a vertical sense. So we can do a vertical scan of the plumes, looking at composition of these plumes, looking at fluid dynamics, and also looking at the composition of the surface, as we may also have a thermal response from the surface. The key instrument in our mission is definitely the mass spectrometer assembly. And in this case, we cannot know a priori which species, which chemical species we are looking for. So we have some assumptions and we have some evidence from Cassini. But we still don't know the whole picture, and we don't know definitely the temporal variability of the plume activity. So what we are proposing is that we will carry a combination of gas chromatography spectrometer, which is a high-level TRL, heritage from ExoMars, which allow us to do isotope differentiation in a rather resolution, and also to look at chirality, those periodic patterns in the carbon sequences, which are expected to have a direct connection to the presence of life. We also carry a tandem mass spectrometer, so this is a technology that is currently at laboratory implementation level, where we can ensure that we will have a resolution high enough to distinguish fatty acids, amino acids that are direct indication of the presence of life. So you see, this so far were key instruments for the questions of habitability, and life. And the rest of the instruments that we carry on board are context, so I'm going to speed up a little bit on this side so we can get to other new developments. I have talked about the shallow and deep sounding radar. Here, the main goal of this instrument is that we can constrain the structure of the cracks under the surface, helping to understand the thermodynamic fluid and how the fluid, the bubbles are evolving into a supersonic flow as they are being ejected from the surface. We have double frequency or double wavelength optical camera, and working also in an infrared channel with a resolution that is already higher than what Cassini has been flying. Magnetometer, as I mentioned, with enough resolution to look at differentiation of dynamo in the mass motion in Enceladus due to tidal forces. And of course, our lander platform. You see the mass spectrometer assembly is integrated in such a way that it will be deployed as a module together with the grain impact analyzer. This is a cone system with a push button. We will see that in a minute. That will allow us to accumulate several samples for which we can have a statistical significance on the composition of these samples. We also carry a microscope, that's the EVA, that's a visible and infrared microscope to look at particle structure, and we have the DICE AI, and that's a new prototype proposal that we are doing here. So this is the push button, the aerogel cubes that will be used to feed the particles in the mass spectrometer. You see the cone collector directly connected at the bottom with the spectrometer that will be pushed in as every particle is being fed to the spectrometer analyzer. We have so-called distributed seismology. Enceladus, I have to check this. Well, it doesn't matter. So acronyms are hard to remember. But basically, we have a distributed set of seismology experiments that are newly designed for this mission. They consist of geophone, mainly, packed in a very compact penetrator package. And the key of this is that we will deploy from the orbiter 3 of these elements that will target soft areas in the surface because we can achieve then soft landing conditions. And it's not a problem in this case to not have a rigid contact with the surface because we have engineered a mechanism. You see these spikes that go up and down. This is a bi-stem system by Lockheed Martin, which is typically used for deployment of antennas and small pieces on the telescopes. And what it will allow us is, on one side, to have a direct connection with the ice interface and a monopole antenna that will go all the way over the snow cover, allowing us to relay the data from the seismometer to the lander. So you can see here a very basic demonstration of how this instrument will be oriented. We can ensure the vertical orientation of the monopole by activating a small pyro that will be fed with an IMU to tell us the gravity vector. And therefore, as the two sides, the two deployable bi-stems are equipped with a monopole antenna, we can ensure that at least one of them will be visible from the surface. So now that we have covered our whole instrumentation package and how we address those science objectives, I would like to give the floor to my colleagues, Victoria and Jun, that are going to give you the cost and the risk envelope of the program.
Thank you, Graziella. So, as you might understand, Etna, our mission is very ambitious and also innovative. But it will answer whether we are alone in the universe. It's a crazy question. Whether life, as crazy as it sounds, found its way in the depth of Enceladus Ocean? This is a very defining question, and of course, it has a cost. So we had several challenges to deal with. First, TRL level. As Graziella told us, we have some low, very low TRL equipment, but we are hoping of the development and production of this material for our mission. These technologies are still maturing. Moreover, we are also waiting for LTG radioisotope power generator, because of long cruise. We will need RTG. We also have the planetary protection issue. Of course, the cost to protect Enceladus of any forward contamination is really important in our design. All those elements contribute to the cost of ITNA mission. This is a new frontier mission. We had a cut cost of $1 billion, but without launch costs and without operation costs. So today, the cost that Explorer team proposed you to answer whether life is unique to Earth is $781 million without the 30% margins of NASA. ITNA mission is very ambitious, but we're waiting for NASA to answer these questions. So I let Yoon present you the risk of this mission.
Okay, thank you. So we've kind of shown that for sure it won't break the bank. But now my job is to convince you that this is not mission impossible. So I'll present some of the risks that we looked at. How we approach this is we use the NASA 5x5 risk matrix. And there are two major categories of risk that we assessed. The first one is implementation risk. So what happens during development which could use up all of our margin in terms of time, cost, mass, and other system budgets. Then is the mission risk. So what could happen during the mission that we need to avoid and mitigate. And how we do this, we looked at all the risks that are occurring, and we identify which ones fall into the red categories, which are really mission critical items. And once we identify those, we use a bow tie analysis mechanism to find out what are the root causes, preventable actions, and if the risk actually happens, what can we do immediately to prevent this from getting worse and worse. So I'll present to you 3 examples of risks that we looked at and how we tackled those. Okay, so the first one is, what if our lambda probes couldn't detect the high frequency data that is needed for the tomography? Well, this could be due to the ground interface not being strongly coupled because the ground is very soft, or the sensor could be damaged on impact, or there is a poor line of sight for communication and you can't actually receive the data very well. So how can we mitigate this? Well, we can map the terrain very well before we land to try and identify the correct region. Or we can try to use a propulsive system with a bit of larger margin to land in the correct base. Or we can use an even longer extendable antenna so that no matter what, it can always communicate with the lander. What happens if it really can't detect the data, then the information? Then we can also use multiple probes to increase the probability of collecting the data correctly. So as you can see in the top corner, we have gone from a yellow risk region to a green low risk region. The second example I want to go through is landing in the dark. Because originally we want to, of course, land in the light where we can see everything nice and well. But if there's a program delay, then there's a little bit of a problem because it's now dark and maybe we can't see in the dark. So one of the mitigations, if this happens, is to install the thermal camera and a LiDAR system, and of course try to have a little bit more of a time margin when we're scheduling the project so that we actually launch on time. Now the last example I want to give you is sinking the lander. So by this, what I mean when the lander lands it lands into a very soft surface and starts sinking. So we really don't want this, because what are the consequences? Either it rolls or it becomes a submarine. And nobody wants a submarine.
Well, we do.
At the moment, we've tried to avoid creating a submarine, and we can look at some of the causes. Well, what if the lander is not buoyant enough? We can install some buoyant landing feet, and if the surface is too soft, then we can have some larger landing feet. You can see in the CAD model, the feet is quite large, and we've done some calculations to look at the pressure and the forces to make sure that even if the snow is 90% not dense, we can still land. And what is the mitigation action if really we start to submerge? Well, maybe we can have some emergency procedures where we fire up the engines and quickly go to a different landing zone nearby. So in summary, we've looked at a lot of different risks on the project. Here are some of just the major mission and implementation risks. And you can see beforehand, there was quite a lot of yellow things, red things that we really needed to tackle. And after we looked at all the root causes and preventable actions and to address them, then most of them are green. So this means the mission can go. I will now pass on to my colleague who will talk about the education and public outreach.
Hello, everyone. So, last but not least, we would like to share with you our key strategies for educational and public outreach. In the first place, we want to drop some science questions. The first is, as we say in our first goal, how does Enceladus provide habitable life conditions? And then our second goal is how biotic and abiotic signatures characterize Enceladus. So in order to do that, yes, in order to do that, we want to establish some strategies oriented on utilizing the social media platforms that NASA already have to engage the public, because we believe that science has to be shared. And also to develop different programs, internships, and partnerships so we can continue developing researching and providing new opportunities for the young people like us to keep developing interest and love for space. So now I'm going to pass the microphone to Ariel, who is going to give the conclusion of our mission.
Today, our team has been honored to share with you an innovative and exciting yet safe and feasible mission to explore another ocean world. ETNA is proud to boast the collaboration between 9 countries across the world. We are also addressing the diversity and inclusion goals of NASA by involving collaborators, COIs, and PIs that are from historically underrepresented groups. And we did an okay job of involving next-gen people, because we're all next-gen people. ETNA will directly address the priorities that NASA has set out in its most recent decadal survey. And we're very excited by the opportunity to not only take orbital samples, but land on another ocean world for the very first time to sample oceanic material and also to constrain the internal structure and the driving energy forces that have made this exceptional body. In Greek mythology, Enceladus was known as one of the giants, born to Gaia, the earth, and Uranus, the sky. The giants fought Zeus in an epic battle for control of the cosmos. And Enceladus was struck down by the mighty Athena, not Silenus. And Enceladus was buried beneath Mount Etna, where this giant is trapped today, fighting its fate with earthquakes and volcanic eruptions. Enceladus, his body lightning-scarred, lies prisoned under all, so runs the tale. Over him, gigantic Etna breathes in fire from the crack and seam. and if he haply turned to change his wearied side, Trinacria's isle trembles and moans, and thick fumes mantle heaven. And the nations far away are watching with eager eyes. They talk together and say, tomorrow, perhaps today, Enceladus will arise. I'd like to bring up the rest of my team to thank everyone and engage the panel in questions.
All right, so same format as before. We'll see the jury ask questions first, and then if we have a bit of time, we can have questions for the public. All right.
I will speak very slowly. No, spectacular job. Thank you very much for all your work over the last week. It was nice to meet you all on Wednesday, and it was very impressive to see what you've all done here today again, so thank you. I guess my question is on the lander. You've got your primary core lander, and you've got your 3 sub-landers that come off. I was wondering if you could talk about how you detach those the sub-landers from the main lander, what their propulsive strategy is for moving away from the primary lander, and is there any sort of way, do they just hit the ground and penetrate, or how does that work? Can you go into some detail?
Yeah, so the probes are spin stabilized, and that's kind of why it's symmetric. We wanted to kind of minimize the technologies that are going on this probe as much as possible, so there aren't any propulsive elements on it, and it's going to be impacting the ground from the bottom end because it is spin stabilized. We looked into several options for what we can use as shock absorbers in case it hit hard ice. We found several options that look pretty promising, so if it does hit a hard surface, it should kind of either hit and bounce off or hit and kind of stay there. Even if the probe lands sideways, the communication, the antenna can still extend out, and we should be able to communicate with it. If we land in a soft surface, it should embed itself such that when the antenna and the truss come out, it should be able to make contact with the ground. But we really wanted to simplify the propulsive side as much as possible. Yeah, it's kind of full of instruments and not much of the supporting equipment.
Okay, thank you.
By the way, both groups did an amazing job for what you've done in about a week. It's truly amazing, and the jury is very impressed. Can somebody explain your cost model? For instance, did you do any kind of a sanity check on a bottoms up? If you just add the cost of the instruments and the cost of these things and those things, do you get close?
That's the question I worked for the week. So we did 2 models. So the first one, we took previous missions, like orbiting missions and landing mission, took the cost, the total cost and the mass, and tried to fix out like the mass ratio and budget ratio to have like a rough idea of the budgets. And then we use a cost estimator, functional cost analysis for spacecraft for mission analysis design, using functional relationship for spacecraft design. So it uses only the mass, in fact, mass and inputs from the system engineering team, and then make recurring and non-recurring costs. And we had the big issue of margins for our TRL equipment and also the RTG, as I said before, because it's quite expensive. Like, it's really expensive. And so we found that in 2025, the RTG cost would be for 3 RTG, $117 $, and we make some cost with this. Yeah. So it was quite a lot of iteration between us. We cut some seismic things they wanted to have. I'm sorry about that. So yes, we had some more experiments to make, but we did some iteration in order to have the cost budget like in what we had to be.
can add something like the cost is we have the margin of 30% of the mass, and then on top we have 0.10% delta V margin, and we have power margin, so all the subsystem is oversized in order to consider cost margin, delta V margin, power margin, and yeah. And so all the subsystem, actually, we have margin on all the subsystem, 30%, or it's most, the less conservative case, the delta V margin, it is actually the 10%. But like considering also like the interplanetary delta V and the pump down leveraging trajectory delta V.
So at the short time, I'm forced to ask my toughest question. So with all of the technology development you have to do, you acknowledge you need to do quite a bit, plus the threat of a launch slip pushing you to a dark South Pole. Why should I launch this mission? Why should I start this mission now rather than later?
So maybe I'll answer from a technology perspective, and maybe we can have one of the scientists talk about that. But I think in terms of overall science return, when you lose the light, let's say you lose the light on all of the surface sources of the plumes, you can still do the backlit lighting, and that when you lose the point, you lose all the light. I think, and it's in the plot, is something like 2042. So if we're baselining arrival at 2039, that's 3 years. So let's say if you assume that 3 years is the maximum you want to allow it to push, then maybe you can get there in time to do visual illuminated surface mapping, but then you don't have time to do lander with illumination. But we've sort of talked about the risk mitigation of what do you do if that's the case. So from that perspective, we feel like this architecture isn't so dependent on having illumination. We think it's doable. And I guess from the perspective of science, I don't know if you guys want to add anything, but
maybe I can add something on the So you've got to keep in mind we have an architecture of instrumentation that it's providing context to the mission prior to critical maneuvers as the halo orbit insertion and the descent. What it means is, even if we arrive in winter times, we have radar instruments and UV instruments that are going to be able to characterize the environment and the plume dynamics of Enceladus. And even if let's say the second phase of the mission, which involves the landing and descending to up to 20-kilometer flyby passes, if that doesn't work, if that goes wrong, the knowledge that will be gathered during this mission, especially ephemeris improvement and the characterization of plume activity, will facilitate any other mission that will try to approach pinpoint landing later on. Yeah.
I also want to add, on a science perspective, we looked at the Cassini data to evaluate the region of interest to see if we can't characterize, because we approach Enceladus in the dark, where we still would land to be able to perform that science that does not require the sun.
So from the GNC's perspective, and system engineering's perspective, the system is quite robust in landing because we're using infrared camera. We're quite sure like the temperature is around 200 Kelvin for all the mission duration, so we can land on the upper part of the trajectory is going to be infrared. Then we have the IMU, so we can switch from the infrared to the LiDAR. LiDAR is a very, let's say, high TRL technology because it's been proven on Sirius Rex right now, and infrared camera it has been used in the last maybe more than 10 years. And from a, let's say, political perspective, I suppose like Lockheed Martin would be very interesting in developing like the system we are proposing for the geophones, because it's based on their technology for the boom antenna, so maybe we can do a partnership. So we have like, let's say, a management return in our side and their side. Our judge will be very maybe happy about it.
Okay, I've got a couple, one about the ALICE instrument, and just a quick one. In your delta V estimates, did you include the delta V for the Saturn disposal, which that's not trivial?
We have done the computation actually for the, but let's say we should have maybe 1 kilometer per second delta V in order to do any kind of disposal for planetary protection issue. So I suppose it could be enough to insert ourselves inside the sphere of influence.
You may find it's easier just to run into Tethys, which there's no planetary protection problem there. Not now. Yeah, Tethys might be bummed, but the other is about the ALICE instrument. Is there an occultation port? There is an occultation port. Okay, very good.
So I didn't mention that, but we can do this in an active manner, the imaging, but we can also use calibrated stellar sources in background to look at transmissivity profiles.
Okay, excellent. Also, just a nit on the slide that was up there, it said the range was from 5 to 7 microns, which is at the boundary between near IR and mid IR. Something needs to be fixed there.
Yeah, it may have happened that the last, not hours, but minutes of stress.
Then about something about the sensor requirement. The sensor requirement about the infrared like imaging can be fulfilled by the Gauss camera infrared that we have on board on the lander for imaging like the blue from the lander and then from the space.
People want to make sure you don't have 2 IR cameras.
So just really quick, you guys did a great job. Very inspiring opening of your of the discussion, and I want to go to Enceladus now. So get in line, she says. So one of the things that it looks like you've got a lot of good pieces of the mission and the spacecraft. Actually, the mission feels like it hangs together, but I didn't see a picture of how the orbiter and the lander go together and how the instruments can be used both on the lander and the orbiter, and is there some sort of a clever way that they sit on the launch vehicle as a stack and then maybe they come apart in some sort of a cool way? I just didn't see that. So question is, how does the whole stack go together?
So the primary design driver of that is making sure that we don't have 2 of the mass spec assemblies. So that comes down to making sure that when you attach all of the orbiter instruments and the lander assembly, you need to make sure that what would be an upward facing mass spec collection dish is just on the exterior of the orbiter, such that you can do the fly through the plume and collect samples that way. So from that perspective, you're placing that such that the orbiter only instruments are separate from that assembly, and then the microscope and the geophones are also on that part, and then you can separate those once you go into lander activity. So it would be entirely separate if we could have 2 mass spectrometers, but we're lots of money, lots of mass. It really puts a lot of restrictions. So we think that engineering solution of using it in both contexts is the best way to go forward.
So it's a great concept to save the money on the mass spec, but maybe if you could go back to that picture that was just up there. The question is, and maybe it's a simple answer, is the lander up inside the orbiter as a shell? And could you go back to that picture? It just
Point to which part of the lander.
Yeah, which part's the lander and which part's the orbiter?
It's not
right.
We can't see it.
You cannot see it from here. So the structural idea here, although
there we go.
There. Right. So you have seen the optical instruments are in the opposite face of the lander which includes the mass spectrometer, and it has a meaning because when we want to capture particles, we don't want impacts on the optical lenses. And the idea, although this is very conceptual at the moment, and how to distribute the things, is that we will have then propulsion of the lander on a 90-degree plane with respect to the main thruster, main propeller of the main spacecraft. Therefore, totally disconnected from the main engine and the fuel tanks from the main body. And it will be deployed pretty much in a way as Mascot does on Hayabusa, or Philae has done on Rosetta, as a cubic unit that is detached in orbit. They follow then a phasing in the same altitude, and when the orbiter has left, then the descent maneuver is initiated. That's a concept as far as we were able to get in the frame of time we were given.
That's great, thank you, that clarifies things.
Like having one instrument from one side and another from the other side is not actually a problem, because actually nominal conservative operation implies using one instrument per time. So we don't have any issue about like collecting like simultaneous measurement. This is actually what Rosetta did during Cassini did during the whole flight bars and so on.
Great, thank you. Okay, it's your turn.
My turn, all right. I'd like to also echo my congratulations to both teams. You have all really impressed us. I think this is going to be a hard decision. I have a couple questions. First of all, so your mass spec, these are mostly going to be aroma MoMA questions, so warning. I'm assuming you have some kind of a cover when you're doing your deep Titan full of organic molecules aero capture maneuver, is that correct?
Yes.
Yes. Okay. And then you're gonna presumably pop off that cover so you can do the plume capture. But then during your descent of the landed element, is that portion going to be open because you will be spewing hydrazine everywhere, and given the limited gravity, it may take a while for that residual hydrazine to settle? Have you thought about how that hydrazine contamination might affect your sample cone and sort of swamp your signal in terms of organic analysis?
Like actually for the Series Rex mission, they have estimated which is the quantity, which is the pollution of the sample that they have using hydrogen trust, and this is actually not important for like sample return and for studying. I mean that type of molecule. That further study might be done of this molecule, obviously. But we have a baseline to start with and to go further.
Okay.
Can you go to the mechanism? So maybe we can.
Yeah. So my other question may also help better address this. Could you take me through like a day in the life of an ice grain that you sample at the surface?
Right. So can we go then to the orbiter description, or perhaps even the lander, because then we have all the setup there. It's easier. Yeah. So you see on the very top there is Japa. So Japa is inheritance from Jada on Rosetta. We have renamed basically dust to particle because we expect ice particles. And the idea is that a particle that is with the flow being captured into our collector, that's the cone structure over here, will be fed first of all into the grain analyzer. So this will be a characterization of morphology of the grain, microscopy imaging on a piezoelectric plate. So we will get the whole structure at macro level of the particle.
And you're going to keep that cold to prevent melting or sublimation. How?
Well, if I say correctly, the MSMS spectrometer incorporates a cryocooling system.
Good answer. Okay, keep going.
Right. So then we're going to feed this into the GCMS. Please don't ask me to repeat it.
Oh, you're good. Keep going.
Yeah. And that's where we are going to basically do the first characterization with the rough resolution on carbon, hydrogen, nitrogen mass levels. I think I
And
may
this
get
is-
some help.
Sorry to interrupt. This is from one of those aerogel cubes. Is that where, like, where is the sample and how is it ionized and brought into the GC?
Right. So we have a slit basically of grids 10 by 10 of aerogel deposits, and every time we want to do a capture, we will have one of these exposed, and then we will hit the bottom basically and push it into YAPA.
Okay.
So that's the whole way it's gonna be in the aerogel collector. Goes into, after YAPA, it goes into the GCMS, and after this it gets ionized. So we put it into the Orbitrap accelerator with the magnetic field, and then the particles are gonna separate according to charge. And that's how we do the high resolution spectrometry. Yeah. So the flow is collector, YAPA, GCMS, MSMS.
And we can answer the number of nominal sample R3. Actually, battery has oversight with 100% margin to obtain at least 2-week power. So we can target at least 6 samples from nominal operation, but we didn't want to put it as nominal in order to have margin, because we are not considering guidance and navigation power and other type of power like the electronic box for the communication.
Okay. One final poke, because I just still don't understand this yet. So you have the ice grain. How do you get from there to ions in your mass spectrometer? Are you using laser desorption? Are you heating it up? How are you turning that little bit of ice and organics into ions that are now going to be analyzed?
Right. So I ask my science colleagues to jump in if I mess it up. But the MSMS is equipped with a UV laser.
Okay, so you're going to do laser desorption. Okay.
Right, but that's
on top of an aerosol cube that's probably going to desorb also. So I worry that the aerogel is going to swamp your signal, because that's also made out of organics, right? Or silica and probably some trapped organics. Have you thought about sort of the relative sensitivity of your instrument to aerogel-related contamination versus the trace organics you'll be looking for in the grains?
If I remember correctly the number, we have a resolution of 120,000-ish.
That's resolution. I'm talking about sensitivity. If you have one amino acid in an ice grain, and then you've ionized that, but along with it, 1 million ions from your aerogel that are probably mostly silicate or whatever, but it's still going to confound your trap. How are you going to deal with that?
Right. I would say we will need to look into this.
That was a very tough question, though, so I don't want to
All right, I think unless there are any other burning questions.
You guys did so great, though.
I'll ask Team Explorer to stay up here, but let's give them another round of applause first.